Hey guys, today we're going to be talking about doing some more word problems. Today we're going to introduce two new words called the angle of elevation and the angle of depression. Okay, so I've got a picture here that just kind of briefly talks about that because it is a little bit confusing, but as we go through and do the problems, it's really straightforward. So let's say you're looking at a triangle that looks like this, and the angle of depression it would be, let me draw up here. Maybe I'll use a different color. I'll use red instead. So if I draw up here, my angle of depression would be if I was at this red dot and I look down and see something, it would be this angle that is right here. Okay? But the angle of depression is kind of the opposite of that. So imagine I'm down here at the bottom instead, and I'm looking up and seeing something. So my view is up. That's called an angle of elevation. Okay, so if you're looking down, angle of depression. If you're looking up, angle of elevation. That's what's important so far. And then, so let me go over one real quick geometry thing that is going to make actually doing these problems nice, but a little bit strange. So this imaginary line from where your sight starts and goes down is parallel to, and I'll put some little parallel symbols. There we go. It's parallel to the base of this triangle. And since, this is parallel lines cut by a transversal, you go back to a long time in geometry, really what I'm trying to say is that these two angles are congruent. These are alternate interior angles. From right here, again, let me maybe get a different color. So from right here, the angle of depression is actually congruent with the angle of elevation. So what does that mean for everything that we're going to be doing today? For everything that we do today with the angle of elevation and depression, we're going to treat them as the same angle. And what we're going to do is ignore this part. Let me X this out. We're going to ignore the angle of depression being in the top part. Since it's congruent with the angle of elevation, we're going to put all of our angles that they give us down here in the bottom of our triangle, that bottom corner of our triangle. Okay? So as you're doing this, keep that straight. Every angle that they give you for angle of elevation or angle of depression will go at the bottom of the triangle. For example, let's talk about Brian's kite. Again, I'm going to try to draw this. So here's Brian's kite. It's flying above the field at the end of a 65-meter string. So let me draw here. 65 meters. And then the angle of elevation to the kite measures 70 degrees. So let me draw the ground the best I can. And it wants to know how high is the kite above his head. Okay, so the angle of elevation, ignore elevation or depression, all the angles that we're using go down here in the bottom of the triangle, since they're congruent that we just talked about. So 70 degrees goes there. How far is there? How high is the kite above his head? It's not the horizontal distance, it's the vertical distance. So that means now it's going to boil down to using SOHCAHTOA, sine, cosine, tangent, and setting up a ratio. So this is going to be sine because we have opposite x and the hypotenuse 65, so it'll be sine 70 degrees equals opposite x over 65. And then you can solve for x by multiplying both sides by 65. So if I multiply both sides by 65, I'm going to do 65 times sine 70. And that will spit out my answer. So that gives me 61.1. So x is, I already drew x. X is 61.1, and it gives me units. These are meters. Okay? So let's go on, talk about a few other things, two other problems. So from an airplane at an altitude of 1,200 meters. So let me draw the airplane, and its altitude. The altitude is measured straight up and down. That's just how high in the air it is. So this is 1,200 meters. And the plane is up there at the dot. It says the angle of depression to a building on the ground measures 28 degrees. So let me draw that. And the angle of depression, again, don't put it up here. You always want to put it at the bottom of the triangle. It's 28 degrees. Because technically it is up there down from where his vision starts, but that doesn't actually help us because it's not technically an angle in the triangle. So put this angle at the bottom. It wants us to find the distance from the plane to the building. And you could interpret that two ways. You could talk about being the ground distance down here on the ground. I'm going to use the hypotenuse because I think that makes a little bit more sense. Since he's also 1,200 meters above it, that is really the distance between them. So I'm going to use x right there. But you could make a case that it's asking you for the ground distance. Usually it'll specifically say ground distance or horizontal distance. So we'll use the hypotenuse as the distance to the building. So let's go ahead and set up our ratios like we always do. This one is going to be another sign problem because the 1200 and the x, 1200 is opposite, and then x is hypotenuse. So 1200 is opposite, x is hypotenuse. And if you multiply both sides by x, and then x equals, you're going to do 1200 and then divide it by sine 28. I'm running out of room to show all of my work, but you'll do 1200 divided by sine 28. And there we go. So that will spit out 2,556.1 if you round that up. And this is in meters. Okay, let's go talk about the last one. This will be about finding another angle. So this is an airplane takes off 200 yards in front of a 60-foot building, which sounds very unwise. But let me draw. So here is our ground, here is the building. And the building is 60 foot tall. And the airplane is taking off down here. And that distance is 200 yards. And this is 60 feet, because the units will be important here in just a second. At what angle of elevation must the plane take off to avoid crashing into the building? So the plane is going to go this way and obviously does not want to hit the top of that building. And so assume that the plane flies in a straight line and the angle of elevation remains constant until the airplane flies over the building, because technically he could, fly not in a straight line, but for this problem we're just going to imagine that it's a straight line. So here's our right triangle that we're talking about, and again the angle of elevation or depression is going to be this angle down here at the bottom of the triangle. Okay. First, what we need to do is we're going to need to convert all of our units. So you can convert the yards to feet or the feet to yards. I think I'm going to change the yards down here at the bottom to feet, because you want to be using the same units before you do. This is going to be an inverse tangent problem. So this was 200 yards, and there's 3 feet in each yard. So just do 200 times 3, which would give you 600. So now we're working in feet. Okay, and then this is a tangent problem, right? Because this distance right here, up and down, is also 60 feet. So what we're going to do is we're going to do tangent of theta, and we're going to end up doing inverse tangent here in just a second. The opposite is 60. You want to divide that by the adjacent, which is 600. And then to solve, you're going to do second tangent on your calculator and type in 60 over 600. And it will spit out your angle. So this is a very small angle because it's not going to take off at a very, very steep angle, 5.7 degrees. So it's going to have to take off at an angle of at least 5.7 degrees. And you probably want to give yourself a little bit more room than that. All right, so your problems for today are going to be all about the angles of elevation and depression. They're going to be posted on LMS, and please let me know if you have any questions.